Hey, I'm sorry I'm not with you again, but we're going to do lesson 2. And I still don't have my pen, so I'm going to have to write with my fingers, so please excuse that, but it'll be ugly, but it's better than nothing. First thing we're going to talk about is combining radical expressions with products, and as long as they're the same index, you just multiply the bases. The radicands, so the base under the radical. So like on A, I have the cube root of 6 and an understood square root of 2. I can't combine those. There's nothing I can do, and that's all you would say is they can't be combined. But on B, they're both the cube root, so I can simplify. It's the cube root of, and then negative 4 times 2 is negative 8. The cube root of negative 8 is negative 2. And you can, of course, check that on your calculator as well, but you'll need to be able to do it without one. This is some of what you did yesterday in your section 1 notes. Sorry. You will want to split up just like you do with square roots. Simplify the number, in this case 54, and see, because we're dealing with a cube root, what perfect squares go into that. Perfect cubes. And so, in this case, that's why we'll want to know our perfect cubes that we listed yesterday. You can always use that for reference. But this is 27 times 2. And then we have our x to the 5th. So the cube root of 27 is 3. And then I'm left with the cube root of 2, which is not whole. So that's going to stay under the radical. Again, don't forget to copy that index down. And then we say how many times does 3 go into 5? Sorry, didn't mean to make them go away. And 3 goes into 5 once, and so one of them goes on the outside. How many is left over? 2, so I have 2 underneath. And that would be your final answer. I want you to pause the video and try to do B on your own. It might take a while to figure out what perfect squares in it, but if you have that list handy, that would be helpful. So pause it and work on it, and then check back. So hopefully you've already worked it and you're checking back. I'm going to keep my index. 128 splits into 64 and 2. The cube root of 64 is 4. And so I'm going to put that on the outside. And I have the 2 left inside. 3 is into 7 twice. And there's 1 left over. And that would be your answer. If you can't remember your perfect cubes and don't like doing it the way we normally do it with square roots, you can always do your factor tree. And because I'm wanting cube roots, I need to see if I can pull out 3 of something. So I can pull out 3 2s. You have to go all the way to the bottom. 3 2s, and I'm left with 1 2. So I have an orange 2, right? I have 3 of them. I would pull 1 out. So I would have 2 2s on the outside, which makes 4, and my 2 on the inside. So that's just another way to see that if you prefer doing the factor tree. So these are both square roots. So I can simplify the product. I'm going to have the square root of 72 times 10. X cubed times x. And y squared times y cubed. Remember, when you're multiplying like bases, you add exponents. And then sorry, I apologize for the coughing. you can, again, do the tree, or 720, 144, and 5 goes into that. And sorry for that one. And so then we would say the square root of 144 is 12. Leave the 5 in. Square root, so 2 goes into 4 twice. 2 goes into 5 3 times with 1 left over. Now remember, when you have an even index, which we do, it's a 2, and an even power, we need to check to make sure this isn't odd out here, but we're good. So I want you to pause this and do B, and then check back with me. Okay, so I went ahead and multiplied what's under my radicals and added my bases. And so I solved it into 5 and 1575 divided by 25 and got 63, which I know is also divisible by 9. And so that's 2 perfect squares, so I'm just going to do it that way. You might have done it a different way. The square root of 25 is 5, square root of 9 is 3. I'm left with the 7 underneath. 2 goes into 6 3 times, and 2 goes into 7 3 times with a 1 left over. And so then I'm going to finish simplifying that. 5 times 3 is 15. And remember, I had a even index and an even power on the inside, and I wound up with an odd on the outside. That is where I'm going to need the absolute value. So it's going to be 15 x cubed. With a y cubed, it didn't matter because over here I had a 7. So if I plug in a negative there, I still get a negative, and that's fine. So it's only when you have the even power that you pull out and you get odd. Is there a problem? Okay. So now we're going to do combining them with its division. And so remember, you can split them up by taking the square root or whatever root you're doing of the top and bottom, or of the whole thing. Like either way, you can split that either way. So let's try a couple of these. So the easiest thing to do is to first see if they simplify. So I'm going to write it all big together. I have, you can share this step first if you want. So again, for the sloppiness, 18 over 2 is 9. X to the 5th over x cubed. When you're dividing like bases, you subtract. And I get that. And I know the square root of 9 is 3, and x squared, square root of x squared is x. And so we can simplify it that way. And that's probably always the first way you want to try. Definitely the easiest. So why don't you pause this and work this one and then check with me. So I went ahead and said 162 over 3 is 54. And y to the 5th over y squared is y cubed. 54, we dealt with this number earlier, is 27 times 2. And the cubed root of 27, is 3. And I'm left with the cubed root of 2. And then the cubed root of y cubed is y. We don't have to worry about any absolute values because it is cubed. So we're good there. Uh-oh. Yeah. Okay. Sorry. I want you to try this one. It is multiple choice, but you should be able to do it just by working on your own. So try this for me and then check that. Real quick, go back and clarify why we didn't use absolute values on A, because we did have an even index here, 2 and 2, and we got a 1. So that does fit it, but if you go back to the original problem, they were both odds, so you could have negative numbers there, and so that's fine. So you might have been able to get somewhere with especially with your variables, but this This one is not easy to split up, nothing reduces. And so we can actually work this one a little bit differently. I'm going to actually split it. So kind of the opposite of what we did before. I can see that nothing cancels when it's one big radical, so we can split it up. Okay. And so just like we would do on a square root, we want to say, okay, sorry again. So, when we're trying to rationalize denominators, we want to multiply. So if I have the square root of 5 on bottom, I multiply by the square root of 5 because the square root of 5 times the square root of 5 is 5. Because I have two square roots, right? A square root squared cancels. Well, that's the same thing we want to do here. Except we don't have a squared root, we have a cubed root. So we don't need 2 of everything, we need 3 of everything for it to cancel. So I have 112 here. I need 3. So I need 2 more. I have 2 y's. I need 3. I need 1 more. I have 1 z. I need 3. I need 2 more. And again, the reason we're wanting 3 is because we have an index of 3. Whatever you multiply bottom with, you multiply top. I'm going to do my denominators first. So I have a cube root and a cube root. And we know how this should turn out, but let's do it to check and make sure we did it right. So 12 to the first times 12 to the second. I'm not actually going to get a number for that. I'm going to say it's 12 to the third. Great, I'm multiplying bases, so I add exponents. Y squared and y makes y cubed. Z1 and z squared makes z cubed. And then, we'll just keep going with this for now. That the cube root of 12 cubed is 12. The cube root of y cubed is y. Cube root of z cubed is z. And that doesn't look like any of your denominators, but we need to finish the problem. So now we're going to multiply the numerator and say 5 times 144 is 720. I have x squared y z. And so we say what perfect cube goes into 720? Well, 720 is 8 times 90. The cube root of 8 is 2. And so I'm left with the cube root of 90. 3 doesn't go into 2, 3 doesn't go into 1, 3 doesn't go into 1, so all of that stays. And then I have 2 over 12, which reduces to be just a 6 in the denominator. So you wind up with a cube root of 90 x squared y z all over 6 yz, which is answer A. And so again, just as a review, what we did was we had to get out however many of the index was. So I had a cubed root down here, so I had to get 3 of everything, so I just needed however many was remaining. So what is the simplified form of this? If x and y are positive, so you know how to rationalize the square root, why don't you go ahead and do this and then check back. Okay, almost finished. So I rationalized. Now you could do kind of like we did before and maybe not use as many. Like I multiply by the exact same thing. You could not have any y's and it would still cancel. But when you multiply by the same thing on top, I went ahead and pulled out square root of 9 is 3. So I get 3 times 3 y, and then we have our denominator, and 3 times 3 is 9 over 18 is 2. So we can simplify that. And y squared will just reduce to be y, and so we are left with A. We'll work on more like number 5 in the future, but that was a good just start to expose you to that and get some practice.